So our first speaker is Pritish Jetley. He's a PhD student in the parallel programming laboratory. His talk will be about multi-paradigm approach to high-performance scientific programming. Now hand over.
Thank you. Can everyone hear me or? Oh. Okay. Well, thanks everyone for joining us again this workshop. I'm now the senior most student in our lab, so I can welcome all of you as delegates and stuff like that. And this is an exciting year because we have people from what I consider to be the preeminent language groups in the US at least, and therefore by extension the rest of the world. No offense meant to any one of us. I'm also an international student. But, and the idea of my talk is the design of parallel languages. In particular, I'll be talking about a language that is a little different from, well, a set of languages actually for one thing. So that's one distinguishing feature of the work that Cray and IBM have been doing. There's no one general purpose language to do all your parallel programs in. Instead, you have a set of languages. And each one of these is going to be specialized. Therefore, you get this, what is called a multi-paradigm approach to parallel programming. And the idea is that for HPC applications in particular, this is a useful approach. It's productive and it guarantees some performance also. So let me just jump into it right away. I have 60 slides and 30 minutes. All right. So we've already had some conjecture about what the language of tomorrow should look like. It should have support for modularity, not only in that it allows you to put your programs together in relatively independent, self-contained modules, and you should get, but also gives you some kind of composability in terms of performance. So you have these modules; they should be able to overlap the idle time in one with useful computation in another. We need abstractions so that we can get some productivity of programming. At the same time, we do not want to sacrifice performance, and this, I think, is where the runtime system comes in. And it would seem from the previous talks that the future is now, because you already have these languages which are doing, which are able to express parallel programs in a very elegant manner, compact manner. They have these abstractions that have proved themselves to be useful, and they have good performance also. You can see from the last year's HPCC results that they have pretty decent results now. But I think that this is not an endpoint for parallel languages. In particular, what I'm considering for my thesis is how abstract can a language be before it gets too abstract, right? So what is a good level of abstraction for users or programmers who are writing HPC codes? Are they happy with sort of just the general purpose programming language, or do they want data structures and specific parallel programming paradigms that can help them to write applications productively? And the approach that we take is to assume that specialization of languages is the way to go, and that productivity of programming comes from specialization, which in turn comes from the higher level, which in turn gives you higher level abstractions that you can use in your programs. So, for example, it's almost always better to write a tree-based code with a distributed data structure that is already a tree, instead of manually partitioning all of your particles over a set of processors and having them interact with each other to construct a tree and so on. So we want to take away this burden of having to reinvent the wheel every time with a general purpose language that you get today. And this does not only have a productivity benefit, but also a direct performance benefit. That is because if you have a specialized language in which you can express only certain types of programs, then you can make certain assumptions about the execution of those programs, and that allows the runtime system to sort of guarantee certain performance aspects also. And this is not a new idea; it's been done before in global arrays, where you're provided with the relaxed consistency models to improve performance. So the three key ingredients of our approach are summed up in this slide. It's number one, the plurality of expression. So instead of expressing your programs in one general purpose parallel programming language, you decompose it into a number of modules which are relatively self-contained, and you target for each module you choose a language or a programming paradigm or a framework that best suits its or best matches its semantics. This specialization, and this in turn means that each language will be specialized, so that you cannot, of course, express every possible kind of parallel program in a single language. But what that language is designed to do is make it very easy to write certain kinds of programs. And you might be concerned that now I can't express all types of parallel programs in any one of these languages, so what am I going to do? Well, the idea is you have these modules written in different languages, you allow them to interoperate by basing them on a common runtime substrate and providing some sort of data interchange interfaces. And that gives you interoperability, and therefore you regain completeness. So I just like this picture a lot, so I had to include this slide. But the idea here is that you have these modules written in different languages. They're nice by themselves, elegant and compact. And as it so happens, the composition of all of these, which is achieved by basing them on a common runtime substrate, gives you a whole that is more than the sum of its parts. And so, just briefly to outline what all I'm going to talk about here, I'm going to take a number of languages that are actively under development in our lab, and all of these address different parallel programming paradigms. So there are different ways of writing different kinds of programs. We'll get into a little bit of what the motivation is for each one of these languages, and for some cases I'll even address some of the issues that you run into in its implementation and performance. And also we'll look at some example programs just to see what a program written in any one of these languages would look like. That is to say, what would the user have to do, and where are the savings in productivity coming from? So let me begin with the elder brother of all of these little mini languages that I'll talk about in the latter half of the talk, and that's charge. And this acronym, our group is known for its acronyms. I think we'll come with a set of very good ones: Charm++, Charisma, Charge. So even if you don't like our research, you will at least like the acronyms that we come up with. And the idea here is that you give some of the nice productivity features of Java and put them into Charm++. And at the same time, develop a compiler infrastructure that tries to kind of crease out the wrinkles in the Charm++ system. And I'll talk about what these drawbacks in the Charm++ system are that we try to address through a compiler infrastructure. So let's take the first example, which is the fact that you're repeating yourself a lot in writing a Charm++ program, and also there are a lot of mechanistic things that you have to do in order to get a running Charm++ program. So for example, if I have an entry method foo, the class itself is foo, and its entry method that I'm going to talk about is bar, I have to mention it in three places. First of all, the CI file, the interface C++ file, which is the .h file, and of course the code for the method itself in foo.cpv. And notice in particular that I have to declare beforehand what my parallel interface is going to be for each object. Charge just does away with all of this by giving you a single entry method which you can call from everywhere in your charge program. I think I've forgotten an entry keyword in front of the void bar for charge, but that's okay. It can do other things also. This compiler that we have, and which, by the way, is under active development right now. It can do things like decide what pieces of information are needed for a recipient of a message. So let's say you have a message full of particles that you want to send in a molecular dynamics program. And the structure is given by this declaration of a class particle here. It has several fields. You can see position, acceleration, velocity, mass, and charge. Now, let's say that the pairwise entry method is going to use only particle position and charge. Now you can, if you're a Charm++ programmer, in order to not have to send the other fields of this structure which are not used in the entry method, you either write a different message or you sort of have a different set of parameters that you pass in your entry method here. But what charge can now do is, you give it this code where you're only specifying that I'm using particles in this entry method. It can do an analysis of what are the variables, what are the members of the particle structure that are used in this entry method, and only transfer those variables through a specialized pup method so that you get some sort of savings in the amount of data you're transferring. Similar, an often encountered problem actually with Charm++ programs is the disconnect between the syntax that we have and the semantics of that syntax. So you have these 4 invocations, and all of them could have different semantic meaning depending on what you've done in the .ci or the interface file in annotating these entry methods. So for example, the first foo could be a plain or asynchronous entry method invocation. The second could be a local one. The third one could be a sync, and this one in particular is an array broadcast. So you're sending a message to a whole array of elements, not just one message. And the thing is that you have the same syntax for all of these, so it's easy to make errors in your program when you do this. The other thing, another example of this kind of semantic disconnect is read-only variables. So you've declared in your CI file a read-only variable int. In your CPP file, you declare it as a global variable, and then you assign it a value 17. Now, is this a bug? Well, it depends on what the context is in which this variable is assigned the value. If it's the constructor of the main char, then fine. Otherwise, it's a silent bug. I mean, no one will report it, but the values that you're writing to that variable will not go anywhere. So these are the kinds of things that charge can do away with through a combination of syntax and semantic checking before the program is ever run. There are other things also, like doing simple, actually these are very simple optimizations in terms of the compiler infrastructure required, and also basically they're not novel optimizations or novel applications of these ideas. But the thing is that they improve programmer productivity significantly. So if you're doing live variable analysis on your program, you can find out what are the only variables that are going to be used once the program is restarted, and therefore you can minimize the checkpoint footprint of an application. You can also find in the same way the fields that are to be transported. Let's say if you're using an offload device such as a GPU, you can find out what are the variables that are used in the GPU method and transfer only those instead of a larger set of the data. And finally, just it's an improvement in the workflow. So normal Charm++ programs, you have to write a CI file, an interface file, which is the .h, and a CPP file. Then you run the Charm-C compiler, so to speak, or translator on this CI file. It gives you a bunch of decl and def files, which you then compile together and get your C++ application. Charge just simplifies this a great deal, by a great deal. And what you give is a .cj specification of your program, and it will be compiled and linked together correctly to give you a running application over there. So I'm not really going to give you much of an idea of what charge programs look like. I think we've done that in the past, and there is some consensus at least that it looks pretty much like Charm++ programs without the annoying bits, so to speak. So let me go off to the first mini language, or the first specialized language. The first one that we talked about was just an embodiment of the message-driven paradigm. So in as much as it's like Charm++, it can express all sorts of parallel programs. It is complete in that sense. But this particular one, the one I'll talk about now, Charisma, is one that is meant especially for the expression of static data flow programs. And I won't be rigorous here and give you a complete definition of what a static data flow program is, but just to give you an intuition. If you have a parallel program in which the flow of data does not depend on the data itself, then you're well on your way to having a static data flow program. There are other things also, but I don't have the time to discuss them right now. So let me give you an idea of what kinds of applications this specialized language targets. You have structured grid methods, which is something like a stencil computation. You can have wavefront computations like the Gauss-Seidel. Dense linear algebra, LU factorization is the graphic that I have here. Permutation, that is scatter plus gather. This is seen often in transpose-based FFTs. And I'm not sure you can see this multi-grid graphic here. Damn, I spent so much time working on these and they're not visible. But the idea there is just a relaxation and prolongation operation being applied until you get a certain level of accuracy. So all these can be expressed in Charisma. And I'll just enumerate a list of the nice, what I consider to be the nice features of Charisma. It is like its ancestor Charm++, an object-oriented language. And it is up to the programmer to decompose the application, conceptualize it as consisting of a series of parallel entities. That will not be done by the compiler. But it does give you a nice global view of data and control, and maybe I'll talk about that a little bit here. Communication is achieved not through sending messages, but through a more abstract concept of publishing and consuming values. And the language has a nice separation between the parallel structure of a language and the sequential methods that are used to implement the particular algorithms. And finally, there is a source-to-source translator available which converts all of this global specification into a Charm++ program. And so I'll just speed through this so that we can get there on time. And a Charisma program is basically a sort of structured interaction between a number of objects or arrays of objects. These objects encapsulate data and work. And work is done when you invoke an entry method on any one of these objects. So next, the communication between objects is achieved through publishing and consuming values. So let me give you an example here in the yellow box. What is happening is that object 1 is, we are invoking an entry method foo on object 1, and that results in the publication of a particular value p. This value p is then consumed by object 2 through its entry method bar. And this is the specification that you would feed to the compiler, which would then generate the Charm++ code, and you get a running program. You can specify sort of data parallel operations through a for each construct. What we are saying here is that for each index x and y in this set, S, this is the Cartesian product of S with itself, and the set S is basically the range 0 to n-1 with stride 1. So for each set in this two-dimensional index space, do axy.foo. So invoke the entry method foo on each object axy. Right? And so I'll just jump forward. I'm not going to talk about the particulars of the language because we really don't have time. But let's try to see what an LU decomposition might look like in Charm++. In Charisma. And just to give you an idea of what's going on, you have this diagonal element, which will be factorized first, and then you do the active panel updates and the trailing matrix update over there. And this is done. Yes, I forgot to mention that. So each one of these squares is a chunk of data, and it also has some work associated with it, and it is migratable, as Sanjay said. And we do this iteratively until we get just this one thing to factorize. And so in Charisma, what this looks like is you have an outermost for loop. You define an index space of indices, and those are going to define your particular sub matrix that you're going to work on for the factorization for this iteration. And what we do is the diagonal element a sub kk will make a diagonal some value to be consumed by the active panels. We do the active panel updates here, the upper triangular and lower triangular factorizations. These result in the generation of columns and rows for the trailing matrix updates, and that these values are then consumed here, and that's where we do the trailing update. So one thing to keep in mind here is that I'm not showing you any sequential code, chiefly because you cannot put sequential code inside a Charisma orchestration, inside the Charisma specification. That's done separately and is all C++. And of course there are others, but let's not talk about them here. The second language that I'll talk about is another specialized language, and it's meant to express programs that have this form of generative recursion. So let me, without giving you a definition, I'll just give you sort of examples of this kind of recursion. And, sorry, wrong slide. Examples include sorting, so Quicksort, for example. And the convex are some computational geometry algorithms such as convex hull and Delaunay triangulation. And there are others. But what ties these examples together is that they have a recursive structure. So we have a set of elements A upon which we are invoking the recursive function f, and that can be expressed as a composition of the same function being applied to subsets of this array, of this set of elements A. And we would specify this in a functional language in sort of familiar syntax, where we have the sub-problems being solved recursively, and then you combine the sub-problems solutions here in the application of the function g. Now the problem, and maybe I talked about this a little the last year as well, the problem in this kind of a computation is that you have a lot of data movement going on from the input set A to its subsets A1, A2, and so on. And this is not a problem in shared memory systems, but in the world that we live in, distributed memory, this will result in a lot of network communication. So we want to sort of minimize that in some way. And I'll just take the Quicksort example, which you should all be familiar with. But just to recap, what we do is we're given an array A that we want to sort. We find out whether that array is short enough that we can do all of the sorting sequentially. If not, we will do this. And what we're doing here is reading the pivot from the array and use this pivot to partition the array A into 3 subarrays, which are denoted LT, EQ, and GT. So all the elements less than, equal to, and greater than the array. Than the pivot, respectively. And what you do then is recursively invoke Quicksort on the less than elements and the greater than elements, and compose them by concatenating the results. So this seems fine. But what happens is that, let's say we're trying to follow the execution of this divide and conquer program through a number of recursive invocations. In the beginning, you have this large blue array, right, which is spread across many processors, and we select the pivot 129 for the first partitioning. Now all of the elements which are shown in green are less than all the elements that are less than the pivot have to be transported to the left half of the array, which is the LT array, and all the elements which are greater than it must be transported to the right half, which is the GT array. And so this is going to result in a lot of shuffled communication, and this happens at every recursive invocation. So this is what the parallel execution of such a program would look like. You have an input array. It's notionally divided into 2 subarrays, less than and greater than, and that is achieved through an all-to-all communication, basically. The next invocation of the recursive method will again be similar, so less than, greater than, less than, greater than. And again, you keep doing these redistributions, and so there is a lot of communication overhead in the parallel execution. So the idea I had was, what if we can amortize the redistribution costs over several recursive invocations? So you saw that at every step of that recursion tree, there was a redistribution being done. What if we could somehow keep from doing that? And that would reduce the communication overhead that our program suffers from. But on the other hand, it lowers concurrency because you're trying to keep messages from being sent out before they're ready. And so this is a schematic which is not really important, but it outlines the overall approach. Basically, you have a runtime system that is looking at whether or not it is feasible to conduct the redistribution across a large section of parallel processors at every point in the program. And if it feels that it is profitable to do so, then you do your redistribution operation and recursively invoke the same function that you're trying to apply on the output of that. And otherwise, you're in the sequential realm. So you have enough work to do that you can do it you have a small enough piece of work that you can do it in sequential, and so you do that through some adaptive grain size control methods. And like I said before, this allows the consolidation of messages that are being sent to the recursive invocations. Just to show you that I have results, the last year I remember, I give you a nice talk until the end of it, and I said I'm out of time and I didn't show you results, so this time I'll show you results. And I won't explain them except to say that This is the Quicksort execution running on 256 Blue Gene P cores. So you have millions and millions of partitioning events taking place, but what's happening here is that the runtime system is agglomerating all of them dynamically and dispatching them in bulk. So you see this green stuff here is all the bulk application of the partition function being applied. And it's not individual messages being sent, but like a whole, maybe 10 or 1,000 of these together, which are being sent out. There are problems with this, of course. You can see that although we're doing roughly the same amount of work in each one of these green bars, the time taken for it seems to keep expanding. And this is an artifact of the serial data structure that we're using, but it's something to work on in the future. Finally, for my thesis, I am working on a framework for expressing tree-based algorithms. And this has come from my work with Tom and Orion on the Changa n-body simulator, about which you will hear tomorrow. But the idea is that trees are essential in computer science and in parallel computing in several fields. For example, cosmology, of course, but also data analysis in cosmology and in hydrodynamics and stuff. You can use the tree data structure to good effect. And so what I've done for this particular aspect of parallel programs is to devise a distributed tree data structure, which hides a lot of the nitty-gritty and that you don't have to reinvent each time you write a tree-based code. Let me give you an overview of what a tree-based code looks like. So you're trying to do a simulation or write an algorithm in which the spatial location of objects is important. So for example, if you're doing a gravitational simulation, even though each particle notionally has to interact with every other particle, you can devise very clever algorithms which can treat faraway regions of the universe as single points. And therefore, space becomes important. So what you have is a set of particles or data entities that you would like to structure into a tree sort of hierarchy. And that's what is shown here. So you take this input set of particles and calculate some kind of a partitioning across processors on this input set. And the partitioning, it is worthwhile to recall that the partitioning has to be compact in the sense so that space and spatial position of elements is respected. You take that compact spatial partitioning and generate a tree over it. And this is a distributed tree. So you can't have the entire tree on a processor, but you can have pieces of it on the processor. And that's what I'm showing in this graphic here. So you have this global tree, and we have taken little pieces of that tree. So the filled in triangles that you see here are little chunks of the tree, which encapsulate a node and everything beneath it. And you can put them on different processors, or in our case, different chars. And so you can see that in addition to the colored triangles, there are these nodes that I've introduced here. And it's basically the path from the root of the global tree to the root of each one of these tree pieces. That is important. And so if you have this kind of an abstraction, your algorithm basically can be framed as a set of concurrent traversals on the chunks of the global tree. And the way we handle it in my thesis is by using the visitor and iterator patterns. So you have a visitor class which will visit the nodes and do a certain type of computation for each node or each leaf that it visits. And it makes use of an iterator over this global data structure, or the global tree data structure. So it keeps asking for the next node in tree order, or whatever order is defined by the traversal. And it's up to the runtime system to figure out where that thing is located, fetch it, and overlap all the latency that might go into it, and so on. So all of the nitty-gritty is hidden from the user. All the user gets to do is define a visitor and use an iterator to get nodes from the global tree. And I'll skip this because it's basically the model of computation that we adopt. And the nice thing about this is that you can have several objects which are trying to query your data structure, your distributed tree data structure. You can combine these at runtime. You can combine these requests for remote data and make use of a software cache so that you not only reduce the number of remote requests sent, but also increase data reuse. And so just to give you an idea of what code would look like in this particular paradigm, this is actual C++ code that I just lifted from a program that I wrote. And this is, I'm making use of the threaded entry method of charm++ a lot. So you can see the overall control flow of this particular program, which is a Barnes hut simulation. And just very broadly, we have a series of iterations that we want to conduct. So, and in each iteration, what we do is we have a set of particles. We will define a tree on those particles, then use that tree to compute the forces on each one of those particles, move the particles by a certain amount depending on what their accelerations were, and so on. So here I show you the first part of this simulation, where all we're doing really is decomposing the input data set onto a number of chars, or in our case, tree pieces. Then invoke this build method on the tree pieces, on all of the tree pieces, tell each of the tree pieces to build a local tree. This tree is then given to the framework that we have devised, and the framework takes all of these tree pieces together, tries to merge together pieces that are local on each processor to increase the amount of reuse, and then it returns, at which point you can start your traversal on it. So in my case, I have two traversals that I instantiated, a top-down traversal, which is used for gravity calculation, and interestingly, a bottom-up traversal, which is used for smooth particle hydrodynamics. And the chief function that we do in SPH, or smooth particle hydrodynamics, is calculate the neighbors for each particle, and calculate any function can be calculated in that neighborhood and do the averaging. So it's kind of a recursive specification of the algorithm, but the chief operation we do is neighbor finding. And it helps in a neighbor finding algorithm to start from the leaf itself and go up the tree from there and find all the neighbors that are close to you. So that was the long and short of it. Now you just initialize these traversals, tell each one of your tree pieces to concurrently do the gravity and SPH computations, and when you're done with it, you can tell the framework that you can clean up now. I won't use the traversal objects anymore. And so what I've shown here is the black code is all that has to be implemented by the user. The other stuff, the green stuff, is stuff that is taken care of by the runtime system and by the framework. So there are substantial savings in the amount of code that you have to write as a user of this particular framework. Once you've calculated the forces on the particles, you can integrate their trajectories and tell the framework to delete the global tree and start the next iteration. So I'll give you a small glimpse of what the visitor code might look like. I said that we're using a visitor pattern, and what that means is that the object that is going to do the traversal has to define certain sequential methods. And what these sequential methods tell the framework is what action has to be taken when, for example, I'm given a node from the distributed tree. So in the Barnes hut algorithm, whenever you're given a node from the distributed data structure, that is the tree, you try to see whether or not that node is close enough to the leaf of particles that you're doing the traversal for. If it isn't, then you can consider it far away enough that you treat it as a single point, and you can do the gravity calculation with that particular node. Otherwise, you have to tell the framework that I want to keep whatever is underneath this tree. So, or I want to expand this tree node into its children. And you do that by returning a true here. And two more functions that you would define as a user are what to do whenever you're given a local leaf and what to do when you're given a remote leaf. A local leaf is just something that has been found by the framework to be on the same processor as you are. And a remote leaf is something that it has had to fetch from a remote source. So you don't have to do the fetching yourself, but you might want to do different things depending on where a node has come from. And so to conclude this whirlwind tour of what language work we have going on, I'll just give you a brief idea of the final specialized programming paradigm, which is MSA. And MSA stands for Multiphased Shared Arrays. And what that means is you'll be given a global view of a distributed array, and you can treat it as a shared array between several objects, but the sharing is done in a very principled and disciplined way. So you don't have arbitrary reads and writes allowed, and you cannot interleave reads and writes, but rather you have a disciplined, phased manner in which you can do the reads, in which you can do the writes, in which you can do accumulates, and I'll talk about that a little bit. The idea here is, of course, that although you have a global data view of a shared array, you don't always use it indiscriminately, writing and reading at the same time. And this graphic sums up what I just said previously, which is the green squares here represent chunks of a large distributed array, and that array will be an MSA, a multi-phase shared array. The circles that you have are, I hesitate to call them actors, but they're just objects that are trying to do computations, right? They're objects that are trying to do computations, and they communicate with each other by reading from this array, by writing into this array, by accumulating into this array. And when I talked about a principal sharing of this data structure, I mentioned that there are three phases in which you can access the array. So the first is read-only, where any object can issue any read from this global data structure. The second is write-exclusive. So an object can write to any number of places as long as the places do not collide with the places that someone else is writing to also. And the reason we do this is we don't want complicated semantics to decide, or complicated consistency semantics to decide what is and what isn't a valid write. So we just ensure that we don't get into trouble by placing this dictate on the user that if you're writing to an element of the distributed array, you'd better make sure that no one else is also writing to it. So the third and final phase is accumulate. And here we allow a little more freedom or flexibility to the user. So instead of having each object write to just one array, if you have a commutative associative operator that you can apply to the individual elements of the array, then you're allowed to, like you can see, the yellow, purple, and red objects are all accumulating into the same element. But that's allowed because it doesn't matter in which order these operations are applied. Yeah, I'm almost done. And so beneath the covers, what's happening is you have this nice view of global data. You have objects which treat this MSA as a global data structure. The runtime system is going to partition it according to your specifications into a number of chunks which are placed on different processors, and the actual fetching of data from remote sources and all the associated bookkeeping is actually done by the runtime system. So you're free of that. And finally, just to give you an idea of what MSA code looks like, I'm trying to do here a parallel histogramming program. So we declare two MSAs. One is the read-only data that we are going to use. The second one is the set of bins into which we will accumulate the data elements, and that will be the histogram in the end. So the way we do this in MSA is ask the runtime system for a handle to read the elements of A, that is A.get initial read, that should be, I'm sorry for the typo, but you get a read handle in return, and you want to write or you want to accumulate values in the histogram itself, which is the bins array, bins MSA, and you do that by asking the system for an accumulate handle into this bins array, and for each input element that is assigned to this particular object, you just accumulate by getting the bin for that particular next element and accumulating. So notice that there is no messaging going on anywhere. All of that is taken care of by the runtime system. All you specify is this sequential C++ code, and you're good. And there are a number of principal compiler interventions, and this is the last slide. So there are a number of interventions that can be made by the compiler and the runtime system, and a combination of the two. And I will not talk about those here. But in conclusion, there's a lot of language stuff going on, is I guess the main conclusion of this talk. But what we envision is an ecosystem of productivity-oriented and performance-sensitive languages. This ecosystem comprises a set of specialized languages. These languages can interoperate, and through this interoperability and specialization, we give a high-level semantics as well as completeness. And that's where I'll end. Thank you. If there are any questions.
So I see we have lots of frameworks, and is there any plan to to develop something to orchestrate this language? And I mean, if a program has different paradigms, how do we actually ensure the performance?
So I think there are two pieces to that question. One is, how do you write a program with all of these various modules or these various languages together? And I think the answer there lies in the charge compiler infrastructure. So we can have a compiler infrastructure that examines different parts of the program, and they can be delineated as being written in certain paradigms. We can then generate code for them based on these frameworks. The second one is interoperability, and that I guess I discussed to some extent, but not much. But MSA has a key role to play there also. So all of the languages understand what an MSA is, and they can read from and write to an MSA. So that's a means of achieving interoperability.